Hi everyone, this is pre-class video on module 3 of course power system analysis. The module name is symmetrical components. In this module we have introduction to symmetrical components, symmetrical component transformation, phase shifts in star delta transformer, sequence impedances and sequence networks of different power system components, and how to write the sequence network of a given power system, and for different sequence networks we have to find the sequence reactance values. So these are the things we will be understanding in this module. First, in this video I will be explaining the introduction about the symmetrical components and few derivations on symmetrical components. See, the symmetrical components comes because of this problem, that is introduction analysis of unbalanced load against balanced three-phase supply, neutral shift, resolution of unbalanced phasors into their symmetrical components, phase shift of symmetrical components in star delta transformer bank. All these are needed to be understood in these symmetrical components. These symmetrical components we have come across in order to get the solution for the unbalanced system. Unbalanced system is due to the faults in the different scenarios like internal faults or external faults. The fault current is not same in all the three different phases in a power system. So in order to analyze the fault conditions during the different voltage and currents in the phases, we will come across the symmetrical components. Whereas in normal operating conditions in power system, the system is under balance, hence it can be represented as a single equivalent power system. The faults can cause the system to become unbalanced. The unsymmetrical faults we have like line to ground fault, open conductor fault, line to line fault, double line to ground fault, all these. The single phase equivalent system method of analysis using single line diagram cannot be applied for analyzing the unsymmetrical faults. So the problem can be addressed with the help of the this is given by Fortes CL in 1918. This is a powerful technique for analyzing the unbalanced three phase system. Here the Fortes scientist defined a linear transformation from phase components to a neutral set of components called symmetrical components. According to the Fortes theorem, the unbalanced system of n related phasors can be resolved into n system of balanced phasors called symmetrical components of the original phasors. These n balanced phasors of each set of components are equal in length, and the angle between the adjacent phasors of the sets are equal. So that it confines the three phase system under unbalanced system. Here the unbalanced system of voltages or currents can be resolved into balanced system of voltages or currents. These balanced set of components are called symmetrical components of the unbalanced system of voltages and currents. So here let us consider the three phase unbalanced voltages as VA, VB, VC. Since VA is different, VB is different, VC is different, these are the voltages. According to Fortes theorem, these phase voltages can be resolved into three set of components, that is positive sequence component, negative sequence component, and zero sequence component. Let us understand what is positive sequence component. Positive sequence component is nothing but it consisting of three phasors all in equal in magnitude, and they are phase spread from each other by 120 degree, and hence the phase sequence is same as the original phasors. This you can see in this sketch. here we have the positive sequence component. Here we have 3 phasors. All these 3 phasors are equal in magnitude. They are phase spread by 120 degree. They are phase spread by the 120 degree. They have the sequence same as that of the original phasor. That is, ABC is the phase sequence. Here we are measuring the angles in the anticlockwise direction, and naming will be in clockwise direction. Whereas in negative sequence component, here we are seeing the negative sequence component. Here the negative sequence component. Here is also we have 3 phasors. They are all equal in magnitude, but here also the phase spread is 120 degree between the adjacent phasors, but they are phase sequence is not same as the original phasor. Original phasor phase sequence is ABC. Here it follows ABC. Here it follows ACB. That is opposite. So here naming is ABC. Here naming is ACB. ACB. So next we will consider the zero sequence component. Here zero sequence component also consisting of 3 phasors. They are all equal in magnitude, but they do not have any phase spread between. They are in line. They are in line, zero phase displacement from each other. So this is what you will get. This is positive sequence, this is negative sequence, this is zero sequence. This is zero sequence, this is negative sequence, this is positive sequence. When we club these together, we will get example VA1 is here, VA2 is here, VA1 is here, this is from origin 0, then VA2, then VA0 is here, VA0. So the vectorical sum of these will be VA. So VA is nothing but VA0 plus VA1 plus VA2. Like this we can find the unbalanced. Similarly, we can write VB and VC also. So like here only you can consider VB, I will take different color. So VA2, VA2 is here, VA2, VA1 let us VA2, VB1 let us consider VB1 over VB2, go like this, VB2, VB0, then this is VB. Like this we can solve. So here VA1, VA2 and VA0, VB1, VB2, VB0. This is VC, VB, and this is VA. Similarly, VC1 is here, VC1 we have taken in the same direction. Next VC2, VC2 is here down, here VC2 down. Next VA0 is here, VC0, VC0, then vectorical sum of this. So like this we can get the things like unbalanced phasors as VA, VB and VC. From this one can understand that these sequence components, symmetrical components, will give us the unbalanced voltages. That is what it is given here. So the 3 phasors can be written like this. The positive sequence, if you write, this is VA, VA1, VB1, VC1. Okay, this is A, this is A square. What is A? A is a unit vector which on multiplication rotates the another vector through 120 degree in the counterclockwise direction. Example, A is 1 at an angle of 120, B A, okay, A, then A square is A 1 at an angle of 240, A cube means it comes to original position, that is it comes to original position, that is 1, A cube is 1. So this is how we can consider A square, and a cube. You can do the operation a minus a square, you can find a minus a square, you can find, that is minus j root 3 you will get, that is j 1.73 will get. Next a square minus a you can find, that is minus j root 3 will get. Next a square plus a plus a square, 1 plus a square you will get, that is 0. These are the different calculations we can do with operator A. After understanding that, let us rewrite once again the positive sequence components phasor diagram VA1, VB1, VC1. Okay. Then measuring will be in anti-clockwise direction. So naming is this. This is 120 degree, 120 degree. So suppose if I want to, this is the reference phasor. Let us take VA1 as the reference phasor. So suppose if you want to write VB1 is nothing but this from here to here with respect to the reference a square VA1. VC1 if you want to write, that is from here to here, that is in terms of that VA1 is rotated by a times of VA1. So like this one can write VB1 and VC1 in terms of VA1. See, you can see the operator. So here A, operator A, or you can consider it as alpha. So both are same. So A is nothing but 1 at an angle of 120. This is minus 0.5 plus j 0.866. So a square is 1 at an angle of 240. If you put it in this polar form, rectangular form, you will get 0.5 minus j 0.866. So a, if you take conjugate, it becomes a square. So here a, if you take conjugate, that is a square. These are the operators we have, and then a square conjugate if you take, you will get back a. So then a cube is 1. Here alpha means a. 1 plus a square is 0. So this is what I explained in the previous slide. Next we will see the similarly we can represent the remaining phases also. Next, according to Fortes theorem, what happens, then the positive sequence, negative sequence and zero sequence components put together is VA. VB similarly VB1, VB is. So unbalanced phasor VA, VB, VC you can find from the symmetrical components of the individual sequence voltages. That is positive, negative and zero sequence put together will be VA. Similarly, positive, negative and zero sequence of B phase will give you unbalanced voltage VB. So next let us express the above in terms of reference phases. That is, here VA is VA0, VA1, VA2. In terms of VA we can represent VB. So VB1 is nothing but a square VA1. VB2 is nothing but a times of VA2. So similarly we can write this. Example I will tell you. So positive sequence, as I told you, this is positive sequence, VA1, VB1, VC1, this is A, this is A square, positive sequence. So here VB1 is nothing but A square VA1. So VC1 is A times of this. Similarly, the negative sequence is here VA2, VC2, VB2. So like this ACB. Here the sequence is ABC. Naming will be in clockwise. ABC. Here VA2, VC2, VB2. So this is A, this is A square. So that is VB2 is A times of VA2. VC2 is A square times of VA2 from this. From this we can write VB1 as A square VA1, VC1 as A times of VA1. So, by having this we can write the relation between the unbalanced phasors and the balanced phasors. Similarly, one can write the equations in matrix form. Here LHS is VA, VB, VC, and here the constant terms with respect to the operator alpha or A, you can write like this. This is the expression for unbalanced voltages in terms of symmetrical components. Next, let us write this in matrix notation. Here left hand side we have phase voltages A matrix and then Vs. So, left hand side VA, VB, VC. In the right hand side we have two matrix. One is A matrix, that is 1 1 1, 1 A square, all this. Then these are the symmetrical components. Next, if you write the symmetrical components in terms of phase voltages, then we have to consider the inverse of A. The inverse of A is this. So, if you expand that, we are expressing here the symmetrical components, here symmetrical components, that is VA0, VA1, VA2, all these are symmetrical components in terms of, this is A inverse into the unbalanced voltages, that is phase voltages. You can write like this. So, here we have VA0, VA1, VA2, and then constant term 1/3 of 1 1 1 1 A square, 1 A square A, and then here we have the unbalanced voltages VA, VB, VC. So, this is the matrix notation of the three equations. Similarly, one can write the things with respect to the currents. So, in case of the currents, the unbalanced, here you can write these are the phase currents, and we have a constant term, and then that is tau, and then here the symmetrical components of currents. So, here this tau is nothing but 1 1 1 1 A square A, 1 A square. Okay, this and we can express the symmetrical component of currents Is in terms of tau inverse into the phase currents. This is also possible, like in voltages we did. Next, let us consider the three-phase system. Here the three-phase is here we have a line currents IA, IB, IC are the line currents, and line voltages are VAB, VBC, and VCA, and we have the phase voltages VA, VB, VC, and the neutral current IN. So, the symmetrical components IA0 can be written as 1/3 of IA plus IB plus IC, this we know, but in the circuit these three currents are coming, and KCL if you apply at node N, so IA plus IB plus IC, that will be equal to your neutral current. Actually IA0 is IA plus IBA plus IC, that is IA0 is 1/3 of IA plus IB plus IC. So, here this is 1/3 of IN according to the previous formula. So, the neutral current is 3 times of IA0. Next, we will see the derivation of power invariance. The complex power S, the complex power S is equal to VI conjugate always. So, this that is P plus JQ is equal to VI conjugate. Suppose if you write the complex power in terms of phase voltage and currents, VAIA plus VBIB plus VCIC, VCIC conjugate. Next, let us write in this matrix notation like this, and then if you apply, this can be written as S is equal to V, VA, VB, VC, VA, VA, VB, VC, and here IA, IB, IC. This is V transpose and then I phase, VP transpose into, see here, VP transpose into IP. We can write VP as tau PS into Vs, this is what it is written, and IP as tau PS into Is. Simplify this, it is written, simplify, you will get this term. So, if you write the A transpose and A conjugate, you will get 3 times. So, substitute the A transpose and A transpose into A. If you multiply, you will get 3 times of this. If you simplify further, you will get 3 times of this and 3 times of it into I. So, if you substitute for Vs, Vs is nothing but symmetrical component of voltages VA0, VA1, VA2. If you take transpose, and Is is nothing but the symmetrical component of currents, that is IA0, IA1 and IA2. Substitute all that, you will get the complex power is equal to 3 times of VA0, IA0, VA0, IA0 conjugate plus 3 times of VA1, IA1 conjugate plus 3 times of VA2, IA2 conjugate. You will get the final expression for complex power in terms of symmetrical components. With this, I will be ending this video.